All right. So that's some phenomenology. That's kind of baseline phenomenology that we can do with the Hamiltonian, or Hamiltonian derived from our subleading Lagrangian. There's other phenomenology that we can do, and I'll mention some of the most important phenomenology. There's another class of predictions that we can make where we have a lot of predictive power by using the effective theory, and I want to talk a little bit about that. So you can look at semi-leptonic decays, and there's two different types of semi-leptonic decays that you can look at, so-called exclusive decays and inclusive decays. So exclusive is making transitions between the meson states, and inclusive is making a transition where you allow any charm state, not just the lowest order ground state charm, but you could have in this state here, xc, you could have a d pi or a d star pi pi or other things like that. So it doesn't even have to be a single hadron state. So exclusive refers to a particular channel, inclusive refers to a sum over all channels. So the theory in these two is quite different. In this one, you would have form factors for the current between the states. And I already mentioned to you that heavy quark symmetry reduces the number of form factors. You get the single Isger-Wise function. And so heavy quark symmetry is very powerful here. And you can actually also work out 1 over MQ corrections. And people have done that, and it turns out there aren't any. So there's something called Luke's theorem, which actually was a result derived, I think, when Luke was a graduate student, that proved there was no 1 over MQ corrections here. And then you can work out alpha S corrections. And so this kind of, you can just keep going. People have worked out 1 over MQ squared corrections. And this kind of formalism is used to measure VCB, because these decay rates would depend on VCB, and that's kind of what you're after if you're doing this. So you'd like to parameterize and figure out the hadronic physics as much as possible and aid the experiments in getting VCB, and exactly this framework is used. People nowadays, what they do is the 1 over MQ squared corrections need to be computed on the lattice. So lattice QCD computes those corrections. The perturbative corrections need to be computed by continuum people like me. So those are computed. And they put these things together to get VCB from these decays. You could also do it with this inclusive guy. And here, it's more interesting because you can basically do everything with pen and paper. So here you can use an operator product expansion, OPE. And actually, HQET constrains the form of the operator product expansion as well. And indeed, when you work out the leading power corrections, they turn out to not enter until 2 orders down. So again, you're protected from first order corrections, and you just get corrections that occur at 1 over MQ squared. And furthermore, they depend only on the 2 parameters we already defined. So it's not like you even get any new non-perturbative matrix elements. You just get the 2 we were talking over here with the masses. Okay, so there's perturbation corrections, and there's power corrections, but you're actually not even getting any new information relative to the masses, any new matrix elements. Okay, so we'll talk a little bit more about the second one with the OPE. There's a lot of work that's gone into this one, both from the theory side as well as from experiment. So when you think about the decay rate for this b to x sub c L nu bar, it's a doubly differential decay rate in q squared over the lepton pair. So that's q mu. EL you can pick as a second variable. And then you don't know the mass of the state x sub c because it could be different things. It could be a d, it could be a d star, it could be a d pi. So that's another variable. So you have a triply differential spectrum, and you can compute it with an operator product expansion. I'm not going to go through the details of carrying out the operator product expansion. If you want to do reading about that, there's some supplemental reading that I haven't assigned to you where you can read about that in the book Heavy Quark Physics by Manahar and Wise. So for our purposes here, let's think of what operator product expansion means. Is simply that we want to carry out an expansion in lambda QCD over MQ. And if you go into the details, there's an important role played by the fact that you're summing over all states, and that's allowing you to connect the partonic calculations to hadronic calculations, basically by probability conservation. But I'm not going to go so much into that. So when you do this operator product expansion, you can think of it in terms of diagrams. And usually you draw these diagrams as forward diagrams. So here's kind of the matrix element squared. Here's the final state. Here's the B quark going in and another B quark going out. So that's like a matrix element squared. The amplitude squared. And you think about doing an operator product expansion for that. And you match onto operators in the effective theory. And just to give you a schematic structure for those operators. So there's a leading order operator. There's a subleading order operator that has an extra covariant derivative in it. That's kind of what you would do. And then you have Wilson coefficients. The leading order operator here is just B bar B. That's what it turns out to be. This operator here would look familiar because it's D transverse squared. So that's like our lambda 1 operator, and that's where the lambda 1s are going to come from. And then there would be a lambda 2 term, and I just didn't write it. So there's a magnetic guy here, too. So when you look at the leading order operator, B bar B, that counts the number of B quarks. Okay, that's just a number operator. So to all orders in perturbation theory, B bar B is 1. Yep.
How do you cut these? Like you're actually calculating B to K, right?
So you should think of actually looking. So this is a charm quark, and so you would write down that propagator, and then you have a large injection of momentum from the B quark, right? Use momentum conservation and expand the propagator. Thinking about the propagator, if you like, thinking about this guy here having. So you could write this guy's momentum as MBV plus K, all right? And you would expand in K. So at first order, you just drop all the Ks, and that's basically giving you this term. At second order, you'd keep the Ks, and the K squared would be identified with this DT squared.
Right, but how do you cut the effective?
The effective theory diagram, it's already been cut, if you like. So these are this is just a real thing, and I've already taken the imaginary part. So this is all real. Okay. There's no cut to make in the effective theory. The thing I'm integrating out here, so this is a good comment. The thing I'm integrating out here is hard and off shell. So when I go over to the effective theory and I get rid of the off shell stuff, I'm being put on. I have a real part here. There's nothing to cut in the effective theory. sometimes, as you know, there are things to cut in the effective theory, but here there's nothing to cut on this side. Okay, so this is 1 to all orders, so that actually means that we don't even have a non-trivial matrix element here. We just have a Wilson coefficient. So everything in the first order term is completely calculable. No non-perturbative parameter because of symmetry. And this guy here is the power correction. And if you look at what the Wilson coefficient is, so it's a function of alpha s. You could think of it like this if you want. And all the kinematic variables like these guys. And it is equal to the free B-quark decay. Including the loop corrections, of course. So not only the tree level result, but adding loop corrections to the right-hand side here. If you add the loop corrections and you drop all the k squareds, then you get just the free B-quark decay, no non-perturbative matrix element. So you can just calculate that first term, order by order. Just doing a partonic calculation gives you the right thing to describe this decay. And the OPE is telling you that that formally is exactly the right thing. Even if you just started to do it, it's actually technically the right thing to do here. It wouldn't be the right thing to do for the exclusive decays, but it is the right thing to do here for the inclusive. So what is the range of validity of this sort of? Is there any restrictions on these kinematic variables? And there is. We're treating the kinematic variables as if they're hard. And that means basically that we're thinking that they scale like powers of the heavy quark mass. So there can be regions of phase space where that wouldn't be true. But as long as we stay away from those corners, edges, then what I said is right. And it's a little more powerful than that. So stay away from edges. Or there's another way of thinking about it, and that is that you can integrate over regions of the Dalitz plane for the phase space variables. That includes all the way up to the edges. And as long as the size of your integration region is order MQ, then you're also fine. So think of like something with like MB squared up here, DMX squared, for example. And it doesn't have to be exactly MB squared. It could be MB squared over 2, MB squared over 4, something that you're counting as order MB squared. And again, you would be fine with doing this type of operator product expansion. So what happens is if you restrict yourself to be close to the edges, then restricting yourself to be close to the edges introduces new scales in the problem. And if there's new scales in the problem, just having a power counting that separates out lambda QCD and MB would not be enough. We'd have to do more detail. And that there is actually some interesting things that happen there. We probably will talk about at least one example later on when we talk about SCT. OK, so I already said that there's a non-trivial fact happening at NLO. Well, I already implied that there's no 1 over MB corrections. And so that's an important outcome from this result. If you want to derive this, you need the effective theory. You basically use the equation of motion to get that to be true. And then, so this is NLO in the power corrections, and then NLO, as I said, is just lambda 1 and lambda 2. At order lambda QCD squared over MB squared. So phenomenologically, this is actually wildly successful. This is, as far as I know, this is the case in QCD or in any theory where people have actually carried out the operator product expansion in the most detail. So people have gone up to 1 over MQ to the 4th. So they've calculated at least 2 loops for everything and maybe even 3 loops for the NF pieces. So, and experimentally, it's been explored. You have this 3 to death. You have these three variables, and they've constructed of order 80 moments from these 3 different kinematic variables, sliced and diced the decay rate in all sorts of imaginative and crazy ways, and they've really tested that this OPE just works beautifully. Okay, so you can think of that you're getting a consistent picture, 80 different observables, just from a few simple predictions and your perturbative results. You also get VCB. So everything fits together with the framework I've discussed with you, and you get a result for VCB, which I'm not going to write on the board. Okay, so that gives you, I didn't go through the details. I will give you some reading to learn more about this OPE if you're interested. And sort of sees how some of the things I mentioned, like using the equation of motion, how that actually works out. It's all done very nicely in this book, Heavy Quark Physics. But I just wanted to give you a flavor for kind of, with this effective theory, that there's something very useful you can do with it once you have it. And in this case, kind of the main phenomenological thing that you're after is VCB and what I've described to you, but you could also think about B decays where you're looking for new physics. And again, you know, if you can construct how the decay rate is looking, then you can have a hope of finding new physics in the coefficient of those decay rates, effectively in the Wilson coefficients of decay rates. Okay, so we're going to turn to something else, but let me pause and see if there's any questions.
Is this the best way to get VCB?
The two are actually pretty competitive, the exclusive and the inclusive. Basically, because the lattice is doing a good job of the matrix elements that you need in the exclusive. And again, you have a lot of kinematic information you can use from the experiment on the shape. So they're pretty competitive, actually. They agree. I think it's the disagreement is at like kind of the 1.8 sigma level, so they agree. There's an interesting story in VUB. So you could do the same kind of thing, not for a charm quark as we did here, but for a light quark. And then, actually, if you do beta pile nu and you look at the inclusive version of that, you can do the same type of OPE. A little bit different, actually, but you can do an OPE there as well. Then you go through and you get a VUB in the 2 different ways, and the disagreement's at the 2.5 sigma level. Maybe even, yeah. It fluctuates with time, but on average, it's 2.5 sigma. So that's interesting. There's not an understanding of what's going on there. That's more interesting than this one basically agrees.